So next time in class, we're going to look at execution of a piece of code on a parallel machine. We're going to assume that we have three cores or CPUs, each with their local cache, where the cache implements a MOSI, coherent shared memory. And we're going to assume that all those three CPUs will execute the same code. Okay. The initial state of those machines is defined here. We are going to assume that the CPU1 has some kind of local variable called myID that only it can read, and that local variable, maybe it's a special register that you access when you read myID, and that register contains the value 1. CPU likewise has its own myID register set to 2, and CPU3 has its myID set to 3. No big surprise there. We also have two global variables, globally shared variables, and the variable A is initially set to 1, and the variable B is initially set to 0. Furthermore, we define in which order these CPUs start to execute their code, and we define that CPU2 and CPU3, they're going to start slightly ahead of CPU1. Okay? Then we also define what different bus transactions there are. So we say there is a read to share, there is a read to write, there is a write back, there is an invalidate. Those are the possible Snoopy-based cache coherent transaction that we can send around in the system. Now, I want you to try to figure out how this piece of code will get executed by the three CPUs. And I want you to tell me in the coherent world what's going to happen. So more specifically, I want you to fill in a sheet that looks like this, and that tells what kind of bus transactions are sent and what kind of state changes happen. Let's go back and see what this execution actually will do. So all the three CPU will all start to execute, of course, from the top, and they're going to say while the global variable I is not equal to myID. Okay, and they all have different myIDs. So while that is true, they're going to stay in this infinite loop until variable A suddenly reaches the value that corresponds to myID. Then they will go in and they will execute these two statements. They say B equals B plus A, and then they will increment the value of A, the globally shared value of A. And then they will get into another infinite loop and say, while A is not equal to 4, I'm going to stay in this infinite loop. So what's going to happen here is that once the first one to get in here, of course, will be CPU1. Okay, because CPU1 is the only CPU for which this statement holds. So CPU1 and no other CPU will get in here. They will execute, it will execute these two statements, increment the value of variable A, and then get stuck in this infinite loop here. Incrementing the value of A will make CPU2 very happy, because now CPU2 will fall out of this infinite loop up here. It will execute these two statements while CPU3 is still spinning up here. And then increment the value of A once more. So now A is the value 3, which will make CPU3 really excited, because now it will fall out of this infinite loop, execute these two statements, and while it's doing that, the other two CPUs are stuck in this infinite loop. And they will get really excited when CPU3 gets down to this statement and increments the value of A to 4, because that means that the other two will fall out of this loop and can continue execution. And then in this example, it says after some long time, all data that's stored in all the three caches will eventually get replaced. So I want you to tell me what happens at those replacements as well. So once more, just pay attention here that CPU2 and CPU3 are starting slightly ahead of CPU1. So they will at least spin once in this loop each before CPU1 will start executing and declare success here and advance its execution. So the way I want you to fill out this kind of table is, of course, initially, so here we have the CPU action. So here we're going to define some interleaved action. So we're going to say that CPU 2 starts by doing a load A. And then you're going to fill out if there is any Snoopy cache, Snoopy transaction, bus transaction that's generated by that. And in this case, it's going to be read to share of A. And then I want you to say how the state and value stored in the 3 caches is changed. Just put in the changes here. So for that transaction, after that transaction has happened, CPU 1, and this is what I have here is wrong. It should say that CPU 2, here it should say CPU, after this transaction, CPU 2 has the data in state S. It has the data in state S/1. Okay, so the state/value, they should be stored in all of these places. And then you should also fill out which will give the data, if any, as an answer to this transaction. And in this example, it's the memory that gives the data. It's not the cache-to-cache transfer. It comes from memory. Likewise, CPU 3 takes the next transaction, and we have the same error here, a similar error that I have in the previous line. CPU 3 performs load A, which also will generate a read-to-share request because it didn't have A in its cache initially, so it needs to send out the read-to-share request, which, not as it says here, it doesn't change the state of CPU 2, it's changed the state of CPU 3. So that should be, say, S/1 here, and so on. So we're going to go through here, and then we're going to see the next thing that happens is CPU 1 is going to try to do load A, and so on, and we're going to see how this progresses. So if you would like to just think about this, and maybe come prepared to next lecture, we're going to go through this example in some detail.